all of you. My name is Dr. Nagarjuna, Associate Professor, Department of H&S. Today I want to discuss a topic on superconductivity. And what is a superconductivity? When a substance loses its resistance, losses means reduce its resistance, but a current can continue through it without altering its value, without varying the value. This type of phenomenon is called as superconductivity. And another definition is there: when the electrical resistance of substance drops suddenly zero. That type of phenomenon is also called as superconductivity. This phenomenon was first discovered by Caroline Owens in the year of 1911 with the help of resistivity in the experiment of mercury. And it is the diagram you are observing that. He observed that the electrical resistivity of pure mercury drops abruptly to zero. We observe that it's 4.1 value. After that 4.1 to 4.2, very less boiling point. This type of low electric resistivity value observed in a material called as superconducting material. Now these are the basic experimental facts observed in superconducting materials. The first thing is at room temperature, superconducting material have great resistivity. Why? Because in the definition itself, we discussed that at low temperature. And next one is the transition temperature, that denoted with the letter TC. In different is the value is different for different isotopes of elements. At this transition temperature, it decreases with increasing of atomic weight of isotopes. When it decreases when it varies the atomic weights, the value of transition temperature must be decreases. And the superconducting property of a superconducting element is not lost by adding impurities. In the previous class, we discussed that semiconducting materials. And that we discussed we have two type of semiconducting materials. One is intrinsic semiconductor, another one is extrinsic semiconductor. In this extrinsic semiconductor, we are adding impurities to the semiconductor, pure semiconductor. It changes its conductivity. Depending upon the type of impurities, changes the properties. That is called as semiconductor. But in superconductor, there is no varies by adding the impurities. And another fact is there is no change in the critical structure as revealed by X-ray diffraction. In the previous, we discussed in unit number 1, that is quantum mechanics. We discussed the Davison and Germer experiment proof, mathematical proof. We have two cases. One is relevant to de Broglie's wavelength value. Another one is related to X-ray diffraction. And then we discuss what is X-ray diffraction, what is the formula. In this superconducting material, there is no change of crystal structure of superconducting material with X-ray diffraction studies. And another characteristic is the superconductor is characterized by zero electrical resistance. And the definition itself, we discussed that superconducting material has less resistance or resistivity value. And the other property, what is the other property? Is the thermal properties. Thermal properties like entropy, heat capacity, thermal conductance, all are already you are aware in intermediate itself, thermodynamics units. These thermal properties of a metal changes sharply at transition temperature when superconductivity as temperature is low. Thermal properties, low value at temperature. Why? Because thermal properties related to temperature when there are changes lower in the superconducting materials. And next one is the entropy in all superconducting materials. Entropy is nothing but second law of thermodynamics. It is also in normal state in superconducting materials. And again, the thermal conductivity in superconducting material is inversely proportional. Again, inversely proportional in the superconducting material. And next, elastic properties. What are elastic properties? Elastic properties indicates that stress, strain, Hooke's law, all these properties does not change in transition in superconducting materials. And last one is all thermoelectric. And the upper side, thermal properties, this thermoelectric effects, Seebeck effects, these all are also disappear in superconducting materials. These are the basic experimental facts of a superconducting materials. Next, in this superconducting state is defined by two very important factors. One is critical temperature, another one is critical field. Critical temperature is denoted with the letter Tc. Critical field is denoted with the letter Hc. And these are the various values. Critical temperature indicates every metal or every material having certain temperature. On that temperature, it will the at the boiling point and melting point, the state may be changes. That type of temperature is called as critical temperature. This critical temperature varies with various element to element. This is also one of the important property. So one of the important factor, that is the different values of critical temperatures of different elements and compounds as shown in the table. Now, what is the difference between element and compound? Element is pure form. Compound means combined, two or more elements. We observe the different values. The values are critical temperature values. In the left side, you can observe the element values, various elements having various critical temperature values. In the right hand side, various compounds have different critical temperature values. And second one is critical field. Already in the previous slide I said, na, critical field indicates the letter Hc. It can indicate the graph Hc graph drawn in between the temperature, critical temperature, and also critical field Hc. And that we have having Hc1, Hc2, Tc1, Tc2. It is the range Tc1, Tc2. In between Tc1 and Tc2, Hc1, Hc2, the property of superconductive property can apply. The critical temperature value can denote with a, is also this critical field is also called as critical magnetic field. On that slide, give the definition. The minimum magnetic field which is necessary to regain the normal resistivity. In the definition itself, we said that low resistivity. In this critical field, what is that? Minimum magnetic field which is necessary to regain the normal resistivity is called as critical magnetic field, whatever the value. And what value it regains, that is called as critical magnetic field. It can denote with a equation called Hc of T. T indicates temperature. At the temperature, the value Hc of Hc naught 1 minus T square by Tc square, where Tc is the critical temperature, T is the absolute temperature. And in the previous unit, we studied semiconductor. In this unit, we are studying superconductor. Both are conductor name before. Previous name is different, semi and super. Then what is the difference? In this slide, we give three major properties. The first one is a definition. Now, what is the definition of semiconductor? Semiconductor is a type of conductor which has a conductivity value that falls between the values of insulator and a conductor. It is also denoted that semiconductor is a material which is intermediate between conductor and insulator. We studied already. And so what is superconductor? Superconductors are materials that have electrical conductivity value above the conductivity value of a conductor. There is no other two, conductor, insulator, there is no two, only conductor is there. The electric conductivity value is above the conductivity. It is an intermediate value, semiconductor value. Superconductor is a one value. And another difference is electrical conductivity. The conductivity is in between conductor and insulator. In the superconductor is very high compared to conductor. Another important factor is band gap. It is also called energy band or energy gap. The energy gap between valency band and conduction band in a semiconductor is 0.25 to 0.25 and 2.5 electron volts depending upon type of semiconductor or type of energy of a device like p-n junction diode, GNR diode, etc. In superconductor, above 2.5 electron volts is compared to already the definition also said that the value is more than conductivity value. That's why the energy gap is above 2.5 electron volts. It is called as superconducting materials. This is a major difference between semiconductor and superconductor. Students, don't confuse. It is semiconductor and superconductor. Examples: silicon, germanium. Already you know that. These examples are aluminum, niobium, magnesium, etc. This is the major difference between semiconductor and superconductor. And again, what is the difference between what are the types of superconductors? In a semiconductor, we have two types. How do you know that? Pure semiconductor, that is intrinsic semiconductor, and impure, that is extrinsic semiconductor. On that way, these also have two types: type 1 superconductor, type 2 superconductor. Then type 1 superconductor is also called as soft superconductors. Type 2 superconductors are also known as hard superconductors. Why we are called as soft means it can deal with only one critical value or critical value, Hc, critical field. In this type 2 superconductors can deals with two in between Hc1, Hc2. That means two critical fields. Already you see in the diagram in the critical field. That is, these are called as type 1 superconductors. Type 2 are also called as hard superconductors. Next, type 1 superconductors exhibits complete Meissner effect. And what is Meissner effect can show in next slide. This type 2 superconductor shows complete Meissner effect below HC1, that is critical field 1, and above HC2. That means in between HC1 and HC2. And the third one is in type 1 superconductors, the critical field is above HC. HC means critical field, more than critical field value. Then these superconductors becomes a normal conductor. In the superconductor itself, the definition we discussed that the value of conductivity is more than conductivity. Electrical conductivity is more than conductivity value. That's exhibits in type 1. That is like a pure superconductor. The type 2 superconductor exhibits the critical value in between HC1, HC2. That means critical field 1 and critical field 2. In a mixed state, it is also called as vortex state. When after HC2, it comes in normal state. That means in origin, that will be ground state. And third one, resistivity. Then of resistivity of the type 1 superconductor is low. How much value also given in the slide, that is 100 to 1000 Gauss. This is a unit for critical field value. The critical value field is low. And the value of HC2 is very large. Why? Because we're discussing from first point. Type 2 superconductors can explain in between HC1 and HC2. After HC2, it comes in normal state. That's why the HC2 is very large. These type 1 superconductors are the materials such as, these are the examples, aluminum, zinc, gallium, etc. This type 2 are nothing but alloys. All, not all alloys, some of the alloys are related to type 2 superconductors like lead indium alloy, different type alloys. These are the classification of superconductors, type 1 and type 2, soft and hard superconducting materials. Now in the first point, we discuss Meissner effect. And what is the Meissner effect? It also shows the diagram. In diagram A, T is greater than Tc, and second diagram, T is less than Tc. Then what is T? Temperature, absolute temperature. Tc, critical temperature. It, because of a person or a physicist, Meissner observed in the year of 1933 this effect on his name. This effect name is called as Meissner effect. If a superconductor is cooled in magnetic field below the critical temperature corresponding to the field, that the lines of induction are expelled from the material. We observe that from A to B. A to B. The difference we observe that. These are straight lines in A. B. There is a gap expelled from the material. This type of effect is called as Meissner effect. It can be obtained through cooling. That can explain in this paragraph along across the diagram. A shows that a superconductor in normal state and the magnetic lines of force pass through it. But when the specimen is cooled, specimen is nothing but a sample or whatever the material can use for experiment. It is called as a sample or specimen is cooled below its transition temperature. The magnetic lines of force are expelled out of the specimen. Thus, the explosion of magnetic lines of force from a superconducting material. It is cooled below the transition temperature. It can be obtained in diagram B, and that indicates that superconducting material. It is a magnetic lines of force. Clearly observe above the transition, above the temperature, the critical temperature, below the critical temperature. In a magnetic field, this type of effect is called as Meissner effect. We also that Meissner effect is a reversible process. When the temperature is increased below Tc, there is a condition T less than Tc. The flux, magnetic flux suddenly penetrates to specimen and substance comes to its normal state. Then a superconductor is a perfect diamagnetic. The reason is that what is the reason why we give the statement is magnetic induction. We studied that magnetic induction and magnetic materials B is nothing but B in a superconductor is 0. Then we observe that the definition B is equal to mu naught H plus M is equal to 0. Where H is nothing but magnetic field intensity, M is nothing but intensity of magnetization. When the values are 0, H that is equal to 0 indicates M is equal to minus H after by solving. When you introduce susceptibility, where susceptibility chi is equal to M by H. M by H. We have a formula. From above equation, M is equal to minus H. M is equal to minus H can be called as equation 1. Chi is equal to M by H is equation 2. Substitute 1 in 2. Where M is equal to minus H by H is equal to minus 1. Then we observe that this is the maximum value for susceptibility of diamagnetic. Then this superconductor is a perfect diamagnetic material. Acts as a. According to Meissner effect, proves that superconducting material is a perfect diamagnetic. Now we discuss what are the uses of superconductors. In the construction of very sensitive electrical measuring instruments like galvanometers in the laboratories, we observe that galvanometer is a device or instrument to observe the current or voltage or deflections. That's why these are used as a output device. For constructing these galvanometers, we use superconducting materials. They are employed in switching devices. So many of switching devices. In this switching device also, we are using superconducting materials. And used in core of electromagnet. You have said electromagnetic materials. Electromagnetism, Lenz law, Faraday's law, all this we discuss. We will discuss electromagnetism. And that two magnets are there, and that two coils. In between two coils are separated with a core. So for that core can be manufactured with superconducting material. And the superconductors are used for amplifying very small direct current and voltages, less currents. That's why in the first point itself we said that gallanometers, milliamperes, microamperes, millivolts. It's a low voltage, low values. Here we can, using these superconductors, can amplify the value. And superconducting cables can be used to transmit transmit electric power over long distance without resistive losses. Cables, various cables, long distance cables using fiber cables, all these cables. Long distance cables we use superconductor. Why? Because without resistive losses, the signal can transmit. Why? Because having low, it has critical temperature less than power loss using ordinary cables. For that cables we use superconducting materials. Students, observe that these are the various learning resources. I will forward this PPT to you in your student groups. Just click on this, you get the material, PDF material you get. These are the links, various links. Observe some extra material about the superconductors in the website also. These are the various questions you get in the examination. There is a chance to get 4 long answer questions and 2 short answer questions. Now, what is superconductivity? Discuss the temperature dependence of resistivity. The second question is again definition. What is superconductivity? Describe the effect of magnetic field on superconductors. How much magnetic field we can observe varies. Describe type 1, type 2 superconductors. Also, this question is also on that way. Compare type 1 and type 2. Or only type 1. Explain type 1 superconductors. On that table, you can write the points about only about type 1. Or type 2, only about type 2, you can write. Either this type of question or explain only type 1 or only type 2 superconductors. And explain the Meissner effect. Okay, right? Both the concept as well as the equations. This is the scope of long answer questions. And short answer questions. Explain basic properties. We discuss in the third or fourth slide. Whereas experimental facts, thus properties, you can write. Basic properties that do not change in superconducting material. Also same way, but same answer asking the other way. Okay. These are the reference book. You want to gain more information. Modern Physics by R. Murugesan, Asian Publications. Another book is Atomic and Nuclear Physics by N. Subramaniam Richol. Again, Asian Publications. All are available in our college library. Okay. Thank you for listening.